what you're looking at here is a simulation of the formation of structure in the universe. If you look at the very bright points, those points are galaxies. You can actually see some of them forming. They're turbulent disks of gas and dust. And you can see, even though they're not resolved, inside those galaxies, stars are forming and heating up the environment around them. So this is the picture that we're going to build up to at the very end. But to get that, we have to kind of set the stage for why we do it, how we do it, why it's important, things like that. So the title that I've selected for this talk is this: Cosmology, Complexity, Computation. And I picked this title because it's alliterative and I like how it sounds. It rolls off of my tongue. But these are also three of the main ideas that I think are going to be the most important in the coming century of physics. These are words that I chose because I like how they sound, but they also represent the main fields that, in my opinion, are going to be where many of the breakthroughs that people our age are going to make. So I'm actually going to ask if we can hold questions until the very end, because I have a lot of slides and I want to be sure that I get through them all. So let me start with the first of these ideas, cosmology. Cosmology is the history of the universe. It's a story that we tell about what we are and how we got here, and to a certain extent what it's all for. And cosmology is something that humanity has been doing for a lot longer than we've been doing what you might call science. All kinds of cultures throughout history have a cosmology, have a mythology about what the world is and where it came from. This has taken on many different forms throughout history, but always it's been a story about the world that reflects something that everyday people know, like a truth that is relevant to everyone's everyday lives. Like if you asked an ancient Hindu what the world is, they might say, well, everybody knows that the world sits on the back of elephants which rest on the back of a turtle. And everyone knows this because we know the world is ancient. And so it must be supported by very ancient things like elephants, which live very long. Or if you asked an ancient Norse person, what is the world? They would say, well, everybody knows that all of the things in nature are interconnected. So it's like our world is just the branches of a giant tree. But we can adjust these stories over time, and we adjust them according to data. Many ancient cultures noticed that some of the stars in the night sky seemed to move in a way which was different than all of the others. The Greeks called these stars wanderers, or planetes, which is where we get the word planet. And they and many other cultures devised a hypothetical system of rotating spheres where these stars were just kind of a puncture, and they rotated around the Earth, accounting for the weird motion of these wandering stars. Many ancient cultures reasoned that fire rises, and if you drop a rock, it falls. So therefore, the earth must be made of rock, and the heavens must be made of fire, because the fire wants to be with the other fire, and the rock with the other rocks. Back 2,500 years ago, people like Plato and Aristotle were proposing exactly that, and it's not exactly right, but sort of. But as we gather more data about the cosmos itself, we can tell better and better stories. Nowadays, since the invention of the telescope, we've discovered that those wandering stars are, actually worlds in their own right. And just in the past 100 years, we've discovered that many of the very, very distant points of light are like galaxies, like island universes in their own right. This is a photo that's very recent, from just, I think, 2 years ago. Almost every point in this image, except for a few of them that have these diffraction spikes, are distant galaxies. So when I say cosmology, what I mean is just the story that we tell about how it all got here in the first place. This is a story that's been evolving and evolving over time as we get better and better data. So I want to tell you today, for just the next few minutes, about our best story so far, the expanding universe. And to get a grasp of that, we have to start with another really popular story that we tell about physics and phenomena, and that's space-time. Space-time is a really successful story because it allows us to describe a lot of different phenomena in one system. Space-time is this idea where the field, the playground through which all of the matter and energy in the universe moves through, is something that can be deformed, curved and twisted and stretched. And this curvature can account for a lot of the phenomena that we see, including things like gravity. And the main idea behind our current story about the history of the universe is this space-time. And what we think is happening is that this space-time is being stretched. Like, this is a space-time which is three-dimensional, which does deform locally due to the presence of matter and energy, but which on very large scales is being stretched out. This is kind of like having everything on the universe being on the surface of a balloon, where you are like an ant on the surface of the balloon. You can walk in any direction, but while this is all happening, the balloon is being inflated. And so what we see is, it seems like from our perspective, everything in this balloon is moving away from us. When we look out at distant galaxies, we notice that there's kind of this great recession. Galaxies all seem, from our perspective, to be moving away from us. We think that most of them are not actually moving a very significant fraction of the speed of light, or even faster than the speed of light. This is a consequence of the stretching of that space-time. And one of the things that we can see, that we can measure, is that those galaxies which are further away are moving away faster. This is something, many of you have likely seen a plot that looks something like this, where we take those galaxies and we plot their perceived recession speed according to their distance, and we see a relationship. This is the evidence that we have for this expanding universe model. But there's a lot of other things that this model accounts for. That's what makes it a good story. I won't go into all of them here, but this is the picture at the end of the day. The universe is filled with all kinds of stuff. Space-time is filled with all of these different forms of matter and energy, and space-time itself is stretching out over time. This is the picture that we have. There's some modifications that have been made to it over the years, and we know to a certain degree that it is not complete. There are flaws in it that are too great to overlook. But for now, it's a really great story. But we're going to make modifications to it, I bet, over the next century. We've noticed that this expansion seems to be accelerating in the modern day, and we think that very far back in time, at the beginning of the universe, this expansion rate was not anywhere near linear. That at the very beginning it went and exploded and expanded many, many thousands of times all at once. But what I'm interested in talking about today, as I showed you in the very first slide, is not really what's happening with space-time, it's what's happening to all of the matter in space-time. And to think about that, we have to start kind of at the very beginning. Over here, at that very first surface that we can resolve, that we can see. And we have to talk also about quantum mechanics. So if you've heard one of these stories that we tell about what happens around the edge of a black hole, where there's these particle-antiparticle pairs that are constantly being born and annihilating one another, like people have drawn pictures that look like this, where there's one which is born, another which is born, and they crash into one another and annihilate. This is what's actually happening, we think. This is a better simulation of what's going on in a picture like that. We think that all of space, everywhere in the universe, has these microscopic fluctuations in the presence of matter and energy. Things that very soon go away, but which are there, and whose effect we can measure. We can do this in a laboratory. We can measure the pressure between two very close together plates due to this effect. And we can measure in the universe in many other ways. The reason that I mention it here is because this quantum behavior at incredibly small scales, this is what seeds the formation of structure in the universe. We would not be here. There would not be galaxies or stars or planets if it were not for this. Because like I said, in the instant where the universe expands by many orders of magnitude in a single moment, these tiny fluctuations grow to become enormous. And they become small underdensities and overdensities in the matter and energy content of the universe. Hot spots and cold spots in the plasma of the early universe. This is something that we can see. If you've heard of the cosmic microwave background, I know someone asked about this just before. These are the cause of the hot and cold spots that we see. Those quantum fluctuations are forever imprinted in our galaxy from the moment when inflation occurred, where the universe expanded very rapidly. But what I want to spend most of the rest of the time today talking about is how we go from a picture like this to a picture like this. Because although we often emphasize these anisotropies, as they're called, the freckles, they're actually a difference of only like a part in 10,000 of the overall thing. Right? When we look at the night sky, we see that it's like 2.7 degrees Kelvin almost everywhere. And these variations are by like 0.3 microkelvin, right? 1 part in like 30,000 of the overall structure. But what we see today is enormous degrees of difference. There are places of space that are totally empty, where it's really cold, and there's places like the inside of a star where it's really hot. So what I want to talk about today is how we go from that to this. And to start answering that question, we have to start thinking about how do we even measure this in the first place? Like, how do we even know what we're talking about? So if I look at a picture like this, can I see the structure of the cosmos? Well, I argue that you actually kind of can if you squint your eyes, but a picture like this is really insufficient. We want to plot the distribution of galaxies with respect to distance, not just where they appear on the sky. But that's something that we can do. We have very advanced telescopes and data processing techniques that allow us to spot very, very distant galaxies and measure where they are in the sky and how far away they are. And that allows us to make maps like this. This is a map of nearby galaxies. Every point here represents a distant galaxy. And what you might notice is this incredible web-like structure. This is something that we see in the galaxies around us today. But it's kind of hard to see what's happening in the very early universe, right? Once we're looking, billions of light years away, we want to look like billions of years back in time. It's hard for us to resolve individual galaxies. They're very dim, they're very far away. Maybe not as many stars have formed, and they're so far that their light has diminished enormously. But it turns out that we can also measure this structure really far away too. We can look not for light which is being emitted, but light which is being absorbed. So we can kind of play this interesting trick where we look for these incredibly bright objects called quasars. Many of you have taken Astro C10. We talk about quasars a lot. These are the accretion disks around supermassive black holes. They're so incredibly hot that they glow brighter than entire galaxies. So these are things that we can pick out in the very distant sky. And the light from these quasars can be absorbed by the gas of this cosmic web as it travels towards us. When the light passes through this gas, it'll be absorbed. But you might think, Cooper, this is kind of ridiculous. Like, as you said in class, the gas is only going to want to absorb certain particular wavelengths of light. So once all of the light has been absorbed by passing through one of these clouds, you're not going to be able to learn anything about any of the others, right? Well, actually, no. We can use the expansion of the universe to our advantage in this case. Take a look at this animation. As the light is traveling through the cosmos itself is stretching the wavelength of light along with it. So as the light travels, it can be absorbed, causing a dip in the spectrum that you would see, and then the whole spectrum gets stretched out, allowing for light which previously passed through to be absorbed by later clouds of gas. In this way, when we look at the spectra of one of these quasars, we see imprinted the history of all of the clouds of gas that it passed through. We can take a spectra like this, and we can map the regions of the spectra which represent absorption and the regions which don't. And from that, we can see where the clouds are. If we have enough of these spectra, we can stitch them together to create a cohesive picture of the large-scale web-like structure of the cosmos. So at this point in the talk, you might be wondering, why does it look like that anyway? Like I've shown you, talked about the expansion of the universe, and I've just shown you this wonderful structure, this cosmic web. But why does it look like that anyway? Well, To answer that question, we have to introduce some new vocabulary. We have to talk about the next main idea that I wanted to get to today, and that is the idea of complexity. This is a really excellent example. This is what's called a Julia set. It's a fractal. But complexity is a more general idea. And nowadays, the science of complexity is so new that real hardcore scientists do not all agree on what the definition is. So I'm just going to give you my definition, but remember that mileage may vary with this one. But the way that I'm going to define complexity for the sake of this talk is complexity is a kind of structure which emerges from relatively simple behavior. So let me give you an example. What you're watching is a flock of starlings. Now, each of these individual birds is not following some grand design plan. There's no individual leader that's telling them all what to do or how to move. They're all just responding to the movement of their neighbors. But from that simple behavior of just trying not to crash into one another and trying to fly together, they produce this really intricate and beautiful behavior. From their simple behavior, they produce complexity. But this is a kind of a straightforward example that occurs in nature all the time. It's not the kind of structure that we are typically talking about. So let me instead switch to ants. Ants are even stupider than birds. All due respect. They just follow one another. Their brains are so small that they do not have the capacity for the kind of computation that's necessary for advanced behavior. All they do is follow one another around. Here they are shown following one another around in a circle until they all starve to death. But these ants, in the right conditions, can produce really intricate structures just by following one another around and doing the very simple behaviors that they're programmed to do. They can produce enormous amounts of complexity. There's actually one thing that I want to point out from this photo before I move forward. This is these researchers filled a giant anthill with concrete and then dug it up. So you're seeing the negative of where the rooms and passageways for the ant colony was underground. One of the things that I want to point out about this structure before I move on is a very special feature that it has called self-similarity. What self-similarity means is that the structures which appear on large scales resemble the structures which appear on small scales. Here I have this. So if you look in this region of the center of the nest, you see all of these very small chambers connected by very short, thin passageways. And if you look at what those are shaped like and how they're connected to one another, they very closely resemble what you see on the much larger scales as you go out from the center. This is a structure which is self-similar. If I say self-similar, I mean that the structure is recursive. It occurs again and again at various different scales. And this is something that nature loves to do. Nature loves self-similarity. You see these. This is a famous fractal shape, the fern. Each of the fronds of this fern resemble the fern itself. And even the smaller parts of the individual fronds resemble the fern itself, on and on and on, all the way down until you get to the cellular level. This is something that nature really, really loves to do. It's easier to encode this kind of structure in the DNA of an organism. You only have to encode the shape of the structure once, and then you can use it over and over again at various different scales. For instance, another really famous example is the shape of your blood vessels. The blood vessels that flow through your body follow a shape that's like this. Again, your body only needs to encode that information once, and it can use it over and over again. How to design a blood vessel? Just look it up and scale it to whatever the situation you need is. But nature is not the only thing that likes to make self-similar structures. Self-similar structures are not only associated with living systems. You also see them in physical systems. This is, the tiny lightning bolts coming out of these two coils of, I think, pipe cleaners. you can see here pretty clearly that the structures occur again and again at very different scales. This is a self-similar structure too, and it's born from another one of these complex systems. All of the atoms in this system are following their own very simple rules. They're just doing what atoms do, collide with one another, carry electric charge, things like that. But from that very simple individual behavior, you have incredibly complex emergent structure. Lightning isn't the only thing. Take a look at this watershed. Right, this is the pathways in a watershed, like a floodplain, carved by the water that moves through it. You can see that there are these fractal shapes again. You see these pathways that are carved on very large scales resemble the ones that you see on very small scales. This is something that we actually have the kind of mathematics nowadays from fractals that allow us to describe behavior like this. But let me show you another example that's a little more relevant to what we're talking about, and that's from fluid dynamics. Take a look at what's happening here. This is just two fluids flowing past one another. The red fluid is flowing this way. The blue fluid on the top and bottom is flowing that way. On very large scales, you see these giant eddies forming. And within those giant eddies, smaller eddies, and smaller eddies within those. Even though the structure is not exactly the same, like a fractal is, you can use the same kind of physical behavior to describe the very, very large structures as you can to describe the very small ones. The same shapes occur again and again and again at different scales. And we can actually describe these in a rigorous, statistical, numerical way. We can count up, like we could in a fractal, how frequently those shapes occur at the very, very large scales versus the small scales. So if you were to look at this fractal, you could say, well, there's one really, really big one, and within that big one, there's 3 smaller copies, and within each of those, there's a total of 9 smaller copies, and on and on and on. There's little of the very, very big structure, and more of the smaller structure. And the smaller you go, the more that there is. And you can describe this statistically using what we call a power spectrum, or what's shown here is just a linear power law. And this works really well for lots of these complex systems. Here I'm showing you the distribution of storm cycles on the surface of Jupiter. You've all heard of the Great Red Spot, for sure. That's the really big one. But Jupiter is also full of lots and lots of really small structures as well that have the same kind of shape as the Great Red Spot, which are smaller. And there are more of the smaller ones, leading to a distribution which looks like that. The bigger you get, the less of them there are. This is true of all kinds of different physical complex systems. For example, you could make a very similar looking plot for the distribution of solar flares or coronal mass ejections. There's lots of little micro ones happening all of the time on the surface of the sun, but only very rarely do you see Earth-killing giant solar flares. Good for us. This is also true of things like avalanches and things like earthquakes. There's fewer of the really big ones. And in all of these cases, that property reflects the underlying complex systems physics. It's even true of things like stock prices over time. If you look at the shape of these, you see that within the large structures, there's smaller copies. The behavior of these stock prices at large scales is actually very similar to the behavior at small scales. And you can relate the two. You can say that the big structures occur infrequently and the small structures occur more frequently within them. So, okay, now we have some of the language that allows us to describe what we were looking at before. Let's go back to the large-scale structure of the cosmos. This is what we're talking about. This is another version of that simulation that I showed you before, where now we've zoomed out a lot more. In this picture, individual pixels represent galaxies or clusters of galaxies. If I point to a region in this picture like here, that's probably where you would find a few galaxies. In a region like this, where you would find maybe 1 or 2, like the Milky Way and Andromeda. What we're looking at is the incredibly large-scale distribution of where matter is in the universe. Now we have the language that we need to describe this. This is one of these self-similar structures, where the structure at very large scales actually kind of resembles the structure at very small scales. But we still haven't answered the question, why does it look like that? What the heck is going on that makes it look this way? I showed you before, it kind of looks like the inside of your brain. Why is that? What is the actual physics that causes this shape to emerge? Well, I can, give you some intuition. I don't want to spend all day doing lots of mathematical derivation. I want you to walk away with an intuitive understanding of what's going on. So let's just talk about the basics. What are the two forces that shape a structure like this? There's only two that we really need to talk about. One of them is gravity, right? Straightforward enough. All of the regions in the universe which are a little bit more dense are going to attract things to them. Gravity likes to pull things together. So if there are regions of the universe where there's a little bit more stuff than others, well, those regions are going to get denser. They're going to pull on other things and collect more. So gravity is causing kind of like a local attraction. But simultaneously, there's also the expansion of the universe. This is like, depending on the cosmological model that you adopt, this could be due to dark energy, this could be due to inflation, this could be just due to the Hubble constant. The expansion of the universe is in competition with gravity. The expansion of the universe wants to pull everything apart, globally stretching everything out, whereas gravity locally pulls everything together. So why does this create the kind of structure that we see? Well, let me show you another example. This is taken from a video by the Slow-Mo guys. Let's see if I'll play the video. Where they're shooting an egg with a bullet. What do you see? What kind of structure emerges? It'll play again, don't worry. Do you see something similar? Yeah, right? You see the same kind of pattern. There's clumps of stuff and they're connected to one another by filamentary structures. It looks a lot like the distribution of matter or of temperature that we saw previously. Why is this? It's due to the same competing forces. Although the forces themselves are not the same, the competition is comparable. In this case, we don't have gravity playing as large of a role. We have the surface tension in the egg itself. Locally, the egg wants to clump together. This is kind of for the same reason that you can fill up a cup of water a little bit over the surface before it spills, or for the same reason that rain falls in droplets because the droplets all coalesce together. The fluid of the egg has a certain surface tension that pulls it together when it can. But that local attraction is in competition with this global expansion. The impact of the bullet pushes everything apart. And so the result of that competition is a very similar structure. Let me play the movie again. So I'm going to play this again, and I want to ask you the following question. What do you think would happen if the bullet came in with a lot more momentum? Would the resulting structure look different? If the bullet came in and hit faster, with more energy, pushing everything apart faster. I'm seeing nodding heads. Yeah, it would. You would see a different kind of structure. Although the overall shape might be kind of similar, maybe everything would be spread out a lot more. Things would, the individual clusters would be further away from one another, and the filaments connecting them might be thinner. Now imagine if the bullet were not traveling as fast, or the bullet were smaller, it came in with less energy, and this expansion was slower. You might see connections between these nodes which were thicker, or nodes that are themselves closer to one another. This is something that we can express statistically using those same tools that we talked about for the other complex systems, the other self-similar systems. We can describe this overall shape using one of those spatial power spectra, talking about how frequent the size of these different structures are. So can we use that idea to learn anything about fundamental physics? We can. Right? If we can describe what the power spectra should look like, if the universe has a certain relationship between the strength of gravity and the strength of the expansion, and we look out at the real universe and we see that it has that power spectral relationship, then we can say with confidence that, that idea of the relative strength of those two things is probably what we see. So here's how we do that. We take a lot of observations of the actual universe. This is from making maps of where the galaxies are, or from making maps of the spectral absorption of those distant quasars to reveal where these structures are. We can study what the overall distribution of these different shapes is. And we can compare what we see in reality with simulations. We can input different physics at the very beginning of our simulations. Let's try making a universe where gravity is stronger, or a universe where there's more dark matter, or a universe where the acceleration of the expansion of the universe is faster, a universe where inflation lasts longer, a universe where the mass of the neutrino is different. We can try all of these different things and put those as input parameters to our simulations. If we can simulate how structure forms in the universe correctly, we can compare a bunch of simulations with a bunch of different input parameters to what we actually see in reality. And we can basically check, using statistics, the same statistics that we talked about before, which of our simulated universes most closely resembles our actual universe that we live in. Right? In cosmology, we don't have the opportunity to just go into the lab and do it over again. We can't create a whole new universe in the lab and try something different. We have to use the computer as our laboratory and try lots of different things there and compare what we see in simulation to what we see in reality. Doing that, we can get a good estimate of what the actual physics of the universe is. So that brings us to the third big idea, computation. Computation is something that I'm going to define like this. It's a definite procedure for logical calculation. Computation used in that way is actually a much older word than the idea of having one of these like laptop computers, something built of electronics or mechanisms. Back in the day, like in the early days of NASA or during the World War, computers were people, oftentimes women. And what they would do is they would perform these repetitive numerical operations. They would take some kind of input number or input set of data and apply very specific, very precise, very well-defined, predetermined operations on that set of numbers to get a new set of numbers. This could be, the trajectory of missiles, or it could be the trajectory of spacecraft. It could be really anything you want. It's just the practice of doing repetitive, numerical operations to arrive at some final calculation. And for a lot of time, this was done by human beings. It's only in the past century or so that we've delegated this task to what we now refer to as computers. What we mean is electronic computers. And this is an idea that can be broken down to its bare bones. After the turn of the century, people were thinking really seriously about what computation actually is. And during World War II, people reduced the whole concept down to something like this. Just strings of ones and zeros, on or off, and having a simple operation that looks at them all and compares them to one another and changes them. Right? No multiplication baked in, no long division, no working with huge numbers, just ones and zeros. And you can prove that any computation that you would want to do, doing an advanced integral perhaps, could be represented at the fundamental level by something like this. No matter what you want to do, you can write it in terms of things like this. So this is still the foundation of how modern-day computers work. Deep inside your computer is a bunch of ones and zeros. This tool is actually really incredibly powerful. You can use it, as an aside, to prove lots of things about mathematics itself, like whether or not there are statements in math that are true but can't be proved, was proven using these. But I digress. I want to talk about cosmology. So you can scale up the complexity of these computations even just a little bit. Here I have a grid of ones and zeros represented by black and white. And each one of these cells is just comparing itself to the value of its neighbors. and turning itself on or off based upon the number of neighbors that it has that are on or off, applying locally very, very simple computations, just ones and zeros. But from that, you can have incredibly complex emergent behavior, the same kind of complexity that we were talking about before. So computation is a really powerful tool for exploring these complex systems, exploring the kinds of behavior that aren't tractable using mathematics by hand on a piece of paper. Let me return for a second to a previous example. This is a numerical simulation of this murmuration of starlings that we were talking about before. Each of these points represents a bird. It has a position and a location, and it follows just two really simple rules. If you're close to one of your neighbors, if you're too close, turn away. And if you find that you're far from your neighbors, far from everybody else, turn towards them. And from that very simple behavior, you can produce that wonderful, beautiful complexity that we saw before. So, before we get to the end of the talk, I want to answer this question. How do we simulate the structure that we see in the cosmos? Well, I'm not going to walk you through all of the individual machine code. I'm not going to talk about how each 1 and 0 in the underlying simulation talks to every other one. We'll frame it in terms of things that we already have intuition for. So how do we do a simulation like this? Well, we have to answer a bunch of different questions. We're going to start with, what's the input? Where do you begin your simulation? And then we'll talk about how do you actually write the computer code. So let's start at the beginning. The initial conditions, how you begin a simulation like this, you can start with a baby picture of the universe. You can look at the universe as it was 13 billion years ago and say, okay, that's where we're going to start our simulation. Maybe we don't know all of the physics of the Big Bang itself, but we're pretty sure about what's going on at space-time, at least, for everything after the CMB. So we can look at the CMB and say, okay, here's our starting conditions. We're going to start with a universe which is very uniform, except for these individual fluctuations. This is something that's also described with one of these power laws. We look at the structure and we extract what is the relationship between how big the features are versus how many of them there are, or what their amplitude is. And we can look at the CMB and measure this. And we can use that measurement as the initial conditions of our simulation. But how do we actually run a simulation like this? Well, let's first start with the basics, just gravity versus expansion. Right? This is sufficient to produce most of the structure that we see. All we need to use is a bunch of individual points, a bunch of little pieces that have a little bit of mass for every one of them. And each one pulls on every other due to gravity. The further away they are, the weaker that pull. And then we just set them loose in a box. It could be an infinite box or a box that wraps back around on itself. But we set them loose in our space-time and let them pull on one another. Simultaneously, we expand that space-time. We stretch it out. But we don't actually have to stretch out anything in our computer code. Right? All that's changing fundamentally is the distances between these things. So we can just, to simulate expansion, adjust the strength of gravity to reflect how space has gotten larger and how everything is now further apart. If we do this, we get something which is pretty compelling. We start, like I said, with almost uniform distribution of matter, just a little bit of fluctuations here and there, and we let gravity versus expansion play out. And we get the kind of structure that we want, to a degree. But remember that gravity versus expansion doesn't capture all of the physics which is relevant. The physics of visible matter, the stuff that you and I are made of, the stuff that we see when we look out into the cosmos, also has a lot of other behavior. It has fluid dynamics and thermodynamics. We can simulate these too. The way that we do this is we chop up all of space into this grid. And with each cell in the grid, we associate a number of parameters. How hot it is, how dense it is, how fast the fluid at that location is moving. And from something as simple as that, we can reproduce all of this complex behavior. All of the wonderful turbulence going on inside the galaxies, all of the growth of stars and the waves of temperature that they produce. And this is just done by taking fluid in one location and moving it around to others, depending on its velocity. From a simulation like this, we can produce all of the complex turbulent behavior that we want to see in the universe. So this will show you that this wonderful, beautiful picture here is actually made up of individual cells, just like what I'm talking about. And you can simulate thermodynamics and other things like that using this grid-based method as well. But so this is sufficient to give us this kind of simulation. This is great. We can use things like this to study the structure of the universe at pretty large scales and to actually constrain the physics that shapes it, just like we were talking about with the egg. We can make simulations like this, and we can use them to basically measure the relationship between gravity and expansion and all of those other things. But there are some limitations to this. We want to talk about the universe at incredibly large scales. We can see this structure going for billions of light years in all directions. And if we want to learn the kind of physics that shaped the universe when it was really young, we have to study the correlations between these structures at very large scales. Let me use this stick. If I wanted to know what this structure over here has to do with this structure over here, I would have to go back to a time in the universe where those things were close enough together that they could be talking to one another. That would be when the universe was much smaller, like way back then. So if I want to learn what kind of physics was shaping the universe way back then, I have to look at how these structures are related to one another across incredibly large scales. Now, we can do simulations at really high fidelity, simulations where we can resolve the structure that we want to see to the same resolution that we're able to observe it. I showed you a simulation that looks like this. But if we want to make simulations that are the size of the observable universe, that allow us to probe the physics way back in time, there's still a huge challenge that we need to tackle. And that is that making a simulation at this resolution on the scale of the observable universe would require more data, more computer memory than the entire internet uses. It's not something that we can do. Like, we could take this problem to our funding agency and say, hey, we want to make a simulation this big, and they would be like, absolutely not. So we have to get creative. We could try to change the resolution. That would be like making all of those individual boxes much bigger. So we need less data for every megaparsec of space. But if we do that, we get something really ugly. No offense. The fluid behavior needs to cascade all the way down to the small scales. It's one of those self-similar systems. If you cut off the really small scales, all of the energy that would be going into them stays at the really large scales. And so you get a large-scale distribution, which is different. The energy cascade is incomplete. And so we actually cannot use simulations like what you see here on the top, this low resolution, to learn anything at all, because the statistics are wrong at all scales. It's just intractable. We cannot use a simulation like this out of the box to actually learn anything about the universe, because it just doesn't resemble what we actually see. So we finally reached the point in the talk where I will talk about what I am doing here at Berkeley, what my research is. And so my research is about solving that problem. It's about enabling us to make simulations of the universe which are incredibly large in size, but which maintain the kind of fidelity that we need to be able to use them to learn something about the physics that shaped the universe. The way that I do that is using machine learning, kind of the new kid on the block in terms of the physics research world. What I do is I design algorithms that can learn what the physics should be at large scales, preserving the way that gravity works and the things like that at very, very large scales, but adjusting for all of the fuzziness that you get when you cut off the cascade of phenomena going down and down to smaller scales. It's fixing that problem. So I won't talk very much about what the individual algorithm is. But what we're able to do is take a simulation which looks like that, which is otherwise unusable, and correct it to something which doesn't require much data to store on the computer, but much better resembles what we actually want. So let me show you this. What we're able to produce is something which is much better. This is supposed to be animated, but that's all right. Where down here at the bottom, we have the high-resolution simulation that we would want to be able to produce at large scales. But on the top, we have what our algorithm produces, which is 10,000 times computationally cheaper, but which still has the correct statistics. It's using a lot less data, but it still preserves the kind of structure that we need to be able to measure. So we trained a machine learning model in order to do this. We used only very, very small volumes, the kinds of things that we're able to make on our supercomputers without maxing out the budget. And then we took this trained machine learning model and used it to think about what's going on at very, very large scales. We produced a simulation of the universe which is billions of light years in diameter. The largest which has ever been produced that has the kinds of features that we care about. Obviously, you could produce a simulation just with the snap of your fingers. Just draw a box, say it's 5 billion light years wide, and that the average temperature is 2.7 Kelvin. Now you would have the largest simulation of the universe. But this is the largest one that we've been able to make, which has all of the features resolved well enough that we can actually use it for what's called Lyman alpha cosmology, using that absorption line detection method. So this is a simulation which is really enormous. The structure you can't even really see with your naked eye unless you pull it out. And here it is compared to what we're actually able to do using state-of-the-art direct numerical methods, what we were able to do before introducing methods like this. And even inside a simulation like that, individual galaxies aren't well resolved. We're talking only about the very, very large-scale distribution of space. So doing work like this has enabled us to probe the history of the universe at incredibly large scales and incredibly, therefore, old times. We're looking at large scales at what the universe was doing very, very long ago. New telescopes that are being built now will allow us to probe the universe at these kinds of scales. And mastering the complexity that's going on in here, being able to make simulations that capture everything accurately, is what will allow us to tell better stories about the universe and its history. Right now, dark energy is just kind of an idea. It's something that we tacked on because it works approximately. Over the next century, we're going to do better, and this is how we're going to be able to do that. But the work that we're doing is not only relevant for applications, in very esoteric blue sky research like cosmology. It's also something that plays out in ways that are relevant to our daily lives. The world is full of these complex systems. What you're looking at here is a simulation of the carbon dioxide density in the atmosphere. You can see it flashing as the day-night cycle occurs. Power plants turn on during the day, and forests absorb carbon dioxide during the night. The Earth itself is one of these complex systems. Being able to model it accurately will enable us to much better predict things like climate change, understand how to mediate the effects of pollution. But complex systems like this occur everywhere in nature. Your brain is a complex system. The trees outside are systems like these. So building computational tools to help us extract the kinds of relationships which occur inside these systems will enable us to learn a lot about nature and about where we come from. That's where I'm going to end today. Thank you all so much. Okay, so I went a little bit over time. It's now almost 2 o'clock, and we have to give up this room because